Early group of tetrapods and modern amphibians are not part of it. So they're kind of ancestral to modern amphibians. So put them off to the side there. Probably do the same with leptospondylus. Anyway, I just like so. We came up on land and we had this big split here. All sorts of stuff in here is long extinct, but we have two groups that came out and survived. We did amphibians on Friday. They're up on land, not very good at it. They're, in a lot of aspects of their biology, they're more like the animals probably that we think are down here. This other branch went more aggressively terrestrial, and that leads to amniotes, and that's where we are now. So that's this chapter here, the other part of this chapter. Where are my buttons? So let's think about what's happening down here. Think about the niche. We're up on land, and we're diversifying, and it's a period of time. We're in the late Paleozoic, the Carboniferous. It's wet. And the world is covered with rainforests. Okay, that's great habitat for things that are like amphibians today. But let's think about the niche. There were things afoot there. And if we look at amniotes and the origin of amniotes, we had a climate change event. Where we went from that very wet world to a much drier world. And that's where amniotes fit in. Amniotes are about terrestrial living. When we look at their origin, we look at aspects of their biology, amniotes are pretty much about better terrestrial living. What is that? I don't want that, whatever it is. So there's our evolutionary tree. Starting with the lobe fin fishes there at the far end. And kind of a review for everything we've been looking at. Let's just zoom out. Let's take the fishy things out of the picture and just look at tetrapods. And remember, the early tetrapods were goofy things called ichthyostagans. They were really more aquatic, terrestrial only in an emergency. We don't need them anymore. Get rid of them. The true tetrapods, sometimes called neotetrapods, it's a classification we don't need. But these are the truly terrestrial tetrapods. This ancestor started spending a good amount of time on land, maybe most of his time on land, as opposed to these more primitive things which are just up on land in an emergency. So there's that split into leptospondylus and temnospondylus. I rearranged this morning. I keep rearranging this part of it. Let's go this route. This is the route heading towards amniotes. Let me see where that's. Yeah, there we go. Okay. Here it is on another evolutionary tree here. Here's all that primitive stuff, and amphibians, we don't need them anymore. These are the things that, as we transition from the Carboniferous to the Permian in here, these are the things that are going more aggressively terrestrial. Starting with these things called leptospondylus and anthracosaurs, cool stuff, all extinct, but they're founding a new niche. Not founding a new niche, it's a horrible way to put that. They're founding a new anatomy that deals with a new niche, more terrestrial. And that's what leads us to the amniotes. Okay, so this is that primitive ancient stuff, diverse tetrapod groups with a dagger by it. And then coming out of that are the amniotes. Good so far? Lots of big goofy words, I know. So here's my summary. This is I put this together, obviously it's not from a textbook, to present this transition the way I like to talk about it, but there's our early tetrapods. This is the amphibian route. Here's our route towards amniotes. So we're transitioning through here. And this is that Permian, Carboniferous Permian transition where it's like drier, drier, drier. So here's some of those creatures. Leptospondylus and anthracosaurs are what come down to us today. If you try to explore the The literature on these, there's just lots of various opinion over the last 40, 50 years. New fossils, new interpretations, new ideas on these guys. Stuff doesn't matter to us. Let's just talk about this massive diversity back there in the Permian. And it's these guys, there's something in there that founds this new lineage that includes all the amniotes. Remember amniotes? All the reptiles, things we typically call reptiles, and mammals. So, let's clean it up. Here's the living ones. And look across the top here. This is going to be our guide to the amniotes for the rest of the semester. These are things you recognize, almost all of them. Maybe the only thing you're not familiar with is the tuatara. But these are the amniotes. Okay? And you can see up here, these some words you recognize. There they are. Here's the more technical ones up there. But let's make all this our friends as we move through here. We'll move through it fairly, well, on stages. So setting the stage. I already got ahead of myself as usual. Here's our time zone. This is the Paleozoic. And here's this Devonian and Carboniferous. These are wet, dry periods on our planet. And the Permian was much drier and warmer. Had a pretty good. This is where all those things we call amphibians with quotes around them, those early tetrapods were diversifying, the Devonian and the Carboniferous. So there you go, wet and mild. Great habitat if you're a creature with an amphibian-like biology. And then the Permian, cooler and drier. And we have one of those extinction events, not one real huge ones, but an extinction event as we transition to this new period. So, again, if we look at the big picture, the Paleozoic, this old part of Earth here, that's often called the age of fishes. That's when fishes originate and diversify. The post-Paleozoic is really much the age of amniotes. It's our group that dominates, particularly the terrestrial habitats. We go, go from it down here to up in here. Okay, here's some synapomorphies. Here's our evolutionary tree. These are all amniotes. Here's some synapomorphies. Let's look at these. The first one, and the big one, is an amniotic egg. We'll come back and talk about this, but what's important about it is an adaptation to living on land. This is an egg that's a self-contained life support system for the embryo. Got all this, they usually have shells, these the early ones did, all this other stuff inside there, all this goo. These structures allow the embryo to complete its development in a little bag of fluid, amniotic fluid. So this egg can be laid on land, it can be carried around, it can be put in a nest. Doesn't have to be laid in water. In fact, I can't think of any amniote that lays its eggs in water. Everything more primitive to this, and amphibians and fishes and things like that, lay their eggs in water. The other thing is we get a more efficient respiratory system, and we've touched upon this in other contexts, but we have something called negative pressure breathing. And clues in the skeletal anatomy will point to the fact these animals are doing this now. But this is where you increase the volume in the chest cavity, creating negative pressure to pull air in. That's what you do. You pull your diaphragm down. Old-fashioned breathing, we talked about the amphibians, is swallowing air, essentially. So, here's this Carboniferous Permian transition, and we get this group of animals we call anthracosaurs. And others. So what are these creatures? They're up on land. They're amniotes, probably laying amniotic eggs, negative pressure breathing, more sophisticated terrestrial dwellers. The anthracosaurs, yeah, are they proto-amniotes? Are they primitive amniotes? Where do they cross the line? That's not a question that worries a whole lot, but you'll talk about it in your book a little bit. I'm not worried about it. Some examples of them. Some of them were fairly large, a couple meters long. And they were up on land. They weren't particularly good at it, but they were better than things that came before them. Question?
Could you please explain negative pressure one more time?
The what now?
Negative pressure breathing.
Negative pressure breathing. Negative pressure breathing, you expand your chest cavity and the air flows in. Positive pressure breathing, you're forcing air down. Okay? So when you breathe, you pull your diaphragm down, it expands your chest cavity, and the air flows in. Okay? That make sense?
Yes.
Okay. So there's the skull of one of these primitive amniotes. And this is important. We're transitioning into some skull anatomy now. And skulls tell us a lot about what's happening. Now this is one of those proto-amniotes or primitive amniotes. It's a big, clumsy skull. There's not a lot of sophistication there. But that's the starting point. And the skulls, we look at skulls to help us position these creatures in the classification, to understand their anatomy, or their biology. So there's cool patterns in skull evolution, which I want to look at right now. I've got a skull lab later in the semester where we'll get some skulls out and we'll look at some of these features. So I found this online. This is just a great summary of where we're going. This is the amniote radiation. And it's got time scale across the bottom there. So there's our stem amniotes, which are all extinct. And then they gave rise to these various lineages, which went towards mammals. And then all these things we typically call reptiles. And look, all these things we call reptiles, monophyletic group, one ancestor, mammals are separate. But this is a pretty good summary of where we're headed. So, here are some skulls, some amniote skulls. And we worry about 3 different kinds. Okay, anapsid, synapsid, diapsid. See the words here? We're going to go through these as we can all define them. Right? Aspid means arch or bar. And it refers to these arches or bars. You know, in a church, an asp is the part with the arches. I think that's where that word comes from. So, no bars, fused bars or shared bars, 2 bars. Let's look at what we mean by that. So the early amniotes, there they are. There's reconstructions of them. And these are the guys that were pioneering terrestrial living. And they're kind of goofy looking. They're adapting to a cooler and drier world. And they diversify in the Permian. They're a Permian feature. Who was this thing? And what was happening down here? There's that stem amniote, that basal amniote, the primitive amniote. Who was he and what was happening? There's a good candidate for one of the creatures that was down there, Brachiosaurus. Remember, saur means lizard, so we see it in lots of biology words. It kind of looks remotely reptilian. It often is called saurus in its name. I know Brady must be somebody's name. And there's the skull. And this is a classic anapsid skull. You can find that as we go along. That's the primitive condition, an anapsid skull. So this is a feature of the most primitive amniotes. That's this thing here. So that's the primitive feature, an anapsid skull. Let's look at what we mean by that. Primitive amniote, these are anapsid skulls. Right there. And a beautiful little pair of fossils showing great anapsid skulls. All right, let's define that. It's this one over here. And you're noticing a difference, right, in these skulls? Look to the temporal region. This is the temporal region of the skull. An anapsid skull, when we look at the temporal region, it's whole, it's complete, it's solid. There's no holes there. That's anapsid. And what it means is no arches. And I guess, the arch defines the hole. So, this is the temporal region of the skull, right here. And that's what we're focused on with these different kinds of skulls. Why is it so important? Here's why. In the red cross-hatching here, these are the jaw muscles. And the jaw muscles insert on the back of the lower jaw, and then they extend. I tried to block it out there because they extend underneath this shelf of bone to the inside of this bone here. And that's where they insert or originate, right? Who's taken anatomy? Insertion is the part that moves, right? Originate is the part that doesn't move. So insertion, origination. So they move under that shelf of bone from the jaw under here and insert on the inside of this. Okay? And those are the muscles that close the jaw. And that's the primitive condition. An amphibian has this. A primitive amniote has this, the anapsid skull. And it goes two different routes from here. Two different skull types diverge off that original form. And it's two different ways of doing the same thing. And we're going to see this again and again and again. We've got this group over here that leads to mammals. We've got this group here, the diapsids or the reptiles. And in all sorts of things, and this is every time I go through this, oh, there's another one, where we get similar developments happening on these two independent lineages. As mammals diversified and as reptiles diversified, they often came up with similar solutions to the same problem. And here's one of them. Here's the first we'll worry about. We get two kinds of skulls coming out of this. One's called a synapsid skull. It has a single opening down here in the temporal region. And the other one is called a diapsid skull. It has two openings. And you can take that word and say two openings, but actually it means two arches. And it's referring to this bone and this bone. But I like to remember it as two openings. And synapse, I think that means early anatomists thought that the two holes merged into one, and so the arch disappeared. It's a shared arch. I think that's what that's saying, but that's not what we think happened. One opening developed in the synapsids, two openings developed in the diapsids. Good so far? Here's what that means. Here's the primitive anapsid skull. This is a primitive amniote. And there's those muscles again going on to inside this bone here. That was kind of hard to draw on this skull here, but they're inserting here, originating underneath here. All right? And so those are the muscles that are closing that jaw. And here it is. Cut this little guy in cross-section. There those muscles go. Okay? Well, it turns out, as amniotes diversified in two different ways, two different routes, one going towards mammals, one going towards reptiles, this became kind of constraining. And two different lineages came up with a solution to that. And that is to open up the temporal region. And the word for an opening in a bone is a foramen. That's a word you've seen in anatomy, right? Foramen. And so these openings develop, and those jaw muscles aren't trapped inside that shelf of bone. They can extend out and actually curve around, come around the top of the skull. That's the functional significance of these foramen. Foramina is plural, I believe. I can't keep that straight. So, as these early amniotes diversify, these openings develop. So there's the primitive condition, and you can see it side by side, and then cross-section there. That's the response to a need. This was fairly constricting and limiting. This opens up more options for jaw development. It sounds like I make it sound very directional. It's not. It's just the way it happened. And it happened in two different ways. One group of these anapsids developed a single opening, and we call that the synapsid skull. And that leads to a group of animals we call synapsids. And the other side, two openings form, and we call those the diapsids. I've used the word diapsid before, haven't I? That's kind of a broader word for reptile. So there's a beautiful anapsid skull. There's nobody alive today with a skull like this. And look at his temporal region there. So the muscles from the underside of his jaw, back of his jaw, would have been on the underside of this bone here. There's a classic early synapsid skull. The muscles come from the back end of the jaw. They go under this arch here, through this opening, and up to the top of the skull. So we have more muscle mass there, more powerful, more sophistication. It's a beautiful early synapsid skull. We have nothing like this alive today. And there's an alligator with a beautiful diapsid skull. Here's the jaw, there's the back end of the jaw, and here's the two openings. So the muscles in that jaw come up and they can reach around and expand through those openings. We've had a couple, they're tragic and sad alligator attacks on humans, right? In Florida recently. Yeah, these are incredibly powerful jaws. If you move to Florida, be careful. Always sad for the family and the individual who's injured or killed in an animal attack, but then I'm also sad for the animals that take the brunt of that, because there will be a backlash against, whenever it's a bear attack or a mountain lion attack or an alligator attack, backlash against animals who don't know any better. That's off topic. So these patterns tell us a lot. They give us a peek into the functional anatomy of the creature at the time. These jaws were working, but they're not very sophisticated. These were solutions to the challenge of having more complex, more powerful jaws. And one group of animals, one group of these early anapsids went this way, and another group went this way. It's a divergence, two types of animals. Yeah.
So there is no more anapses and synapses alive?
You're a synapsid. There are no anapsids still. This group is extinct. This is a primitive synapsid. There's nothing like this alive today, but you're a synapsid. This is just a very primitive one. We'll look at that in a minute. So there's that divergence. Our anapsid skull, that's the primitive one, and the synapsid skull goes towards mammals. Mammals have a synapsid skull, but it's a highly modified one. The diapsid skull develops, and that founds this huge group here. We good? Okay. So there's that thing. This is our chart, the development there. And here's creatures that have it. So we don't have any anapsid skulls still with us today. We're going to look at turtles in a minute, but that's a little bit odd. So this is the amniote ancestor. This is primitive amniotes. Essentially an amphibian, too. The synapsid skull is mammals and mammal ancestors. The diapsid skull is reptiles, birds, dinosaurs, etc. and their ancestors. So there's an anapsid skull. Stem amniote, or an amniote. Here's just, and that's down here. I'm beating this to death. Here's a synapsid skull. All right? Classic example of an early synapsid animal is Dimetrodon, which is always in a bag. You had a bag of plastic dinosaurs, Dimetrodon was in there. Dimetrodon's not a dinosaur. It's a basic basal synapsid. And it's just a beautiful synapsid skull there with that big opening right there. That synapsid skull leads to mammals. Here's a slightly more advanced synapsid. Big opening right there. Fenestra, another word for opening in a bone. Fenestra. What's the word for window in Spanish? Ventana? Yeah, same root there. And now here's a mammal skull, a modern mammal. Let's go back here for a second. Here's the orbit, the eye, and there's that foramen. They're separate. Here's a modern mammal. Here's the orbit, right here, and that's the foramen, right there. In mammals, they're fused. The orbit and that temporal opening. But this right here, the back end there, that's evolutionarily equivalent to this. And we'll get skulls out in lab and look at this. I can put pictures of skulls up all day, but I think it's really helpful. You hold it in your hand, you can put your fingers into the holes. Say, oh, there it is. So, here's a modern mammal. There's the lower jaw. There's where the muscles go. The lower jaw would be hinged right in here. There's those muscles. So you can see that's the functionality of that opening. It's still there. It's just in modern mammals, that's the opening. That's the orbit. They're fused together. And in you as a primate, boy, it's hard to find it. Here's diapsid, the diapsid route. And that's all these things we call reptiles. And here's a dinosaur. There's the orbit. Oh. Not the orbit. There's the orbit. Sorry about that. I know you were worried about that. There's the orbit. There's the lower opening. The upper opening you can't quite see because it's on the top of the skull. But there's the two openings there. It's a diapsid skull.
What's the other?
That's called the antorbital fenestra. We'll talk about that later. This is a living animal. This is a living diapsid animal, reptile. And there's his orbit. And there's those two openings. I have this skull. We'll get this out in lab. It's an endangered animal from New Zealand. I have a plastic copy of it made by this cool company called Bone Clones. But that's just great because you can put your fingers in those two holes and a third finger poke it into the orbit. Of anything alive today, that's the most beautiful diapsid skull we still have with us. We'll talk about them later. And here's a modern lizard. And as animals diversified and specialized, the clues to their ancestry sometimes get lost or diminished. And this is a diapsid skull, but look at here. There's one of the openings, the more dorsal opening. There's the arch, and there's the more ventral opening. And in modern lizards, the arch is gone. The lower arch is lost through evolution, but that's the opening. There's the lower jaw there. And modern snakes are even more specialized. This is a modern snake. There's the dorsal opening, there's the ventral opening. Oh, both the arches are gone now. So there's the lower jaw. Oh, here's the lower jaw there. So highly simplified structure. If we go back here, there it is in its primitive condition. Lizards lose this piece. Snakes lose both pieces. And there's a bird. Birds are exquisitely adapted for low weight, high metabolism, powerful flying. So there's a lot of simplification in a bird skeleton. Here's his orbit, and there's his two fenestra. They're hardly separated, well, they're not separated at all from the orbit. But evolutionarily, that's where they are. Did that. And there's a dinosaur, a Mesozoic reptile, showing more primitive condition. There's the opening, there's the opening. These are the arches, these bones here, which are sometimes lost in more modern things. Yeah, and I got the orbit right there. All right, there we go. So, just comparing. There's that Mesozoic reptile, dinosaur, and there's a modern lizard. So there's the dorsal opening, dorsal arch, ventral opening, ventral arch, missing here. This is called fenestration. And here's an evolutionary tree from a textbook showing lots more detail than we need, but tracking the openings. Fenestration, again, sometimes these openings are called foramen or foramina, sometimes they're called fenestra. So, this tells us a lot, but nothing is ever as clean as we'd like it to be. There's always the outliers. There's always someone who chooses to be difficult. And turtles are a great example of an animal that's specialized itself into its particular niche and lost a lot of clues to its ancestry, simplified its anatomy. And we look at a turtle skull. This is a turtle skull, a modern turtle skull. There's his orbit. There's his temporal region. There's no openings there, are there? That's an anapsid skull. If you use anapsid with a small a. The descriptive condition is no openings. That's an anapsid skull. But our current thinking on turtles is that these are diapsid animals that closed up those holes. Their ancestor had the openings, but as turtles specialized into their armored body niche, the openings closed in evolutionary time. So it's a diapsid animal with an anapsid skull, using anapsid in a descriptive sense. So turtles just have to be difficult. And they're presently in most classifications put as a diapsid with an anapsid skull. We'll come back to turtles because I like them. And again, we've been evolving diapsids and synapsids since the Permian, and there's just lots of different routes this has gone. Or that's not, but several. There's actually a few more skulls out there that we're not going to worry about because they're really quite unusual. But these aquatic Mesozoic reptiles have a fourth kind of skull called a euryapsid skull, and it's got the opening. It's just in a different place than any that we've seen before. So it's a euryapsid skull, and I'm not worried about the details of that. But it's just the point is, as things specialize into their own niche, sometimes their anatomy changes in ways that confuse evolutionary biologists. And then I was looking for pictures of diapsids online, and I found this website. These are NASA photos from Mars. That looks like a diapsid skull, doesn't it? Obviously. There aren't diapsids on Mars. At least I need better evidence than that. Okay. So, I just like these paintings. I don't know how accurate they are, but they're kind of cool. Remember that the trend in amniote evolution is we're moving away from water, becoming more terrestrial. So here are just some things I was thinking about that, the early amniote. First off is this amniotic egg. These are fossil dinosaur eggs, which is very trendy collectible right now. When people are finding them, putting them on the market, they go for tens of thousands of dollars. But these are amniotic eggs. And again, this egg can be laid in a nest, it can be buried in the sand, it can be carried around. It does not have to be laid in water. In fact, they can't be laid in water. It's a life support system for the embryo. The embryo still does all its development in an aquatic environment, like it were a fish. But instead of the egg being laid in the ocean or in a pond, the egg carries its little aquatic environment with it. And all this other stuff is support for the embryo. And what we have, technically, this is an anatomy class, so I'm not going to do it here. We have these structures, the chorion, the allantois, the yolk sac, and the amnion. And you bring all four of those together, that's an amniotic egg. Fishes have a yolk sac, but they don't have these other structures. So if you look at a fish or an amphibian egg, and there's not a whole lot of difference between the two, an amphibian egg and a fish egg, they're very similar. They have to be laid in water, with some really rare exceptions. They have to develop in an aquatic environment. The embryo has to develop. The amniotic egg can be laid on land, buried in a nest, carried around by the parent. So that moves us away from water. We don't have to crawl back to the water to reproduce anymore, like an amphibian still does today. The eggs, the early ones had shells. You're an amniote, by the way. You just don't lay shelled eggs, right? As a mammal, you're an amniote. A lot of amniotic eggs have shells to protect all that development going on the inside. And the classic example of a parent on a nest with amniotic eggs. One of the things that happens when you have a shelled egg, if you're going to put an egg inside a shell, well, the mother's body makes that shell around the embryo. We have to fertilize the egg before we can build the shell. Right? You can't build the shell once the egg's been laid. You can't build the shell until after the egg is fertilized. So this was in my garden one day. we have to have internal fertilization now. The male has to introduce the sperm to the inside of the female's body. The egg is fertilized, the embryo starts to develop inside the female, and then the shell is built. So amniotes have to have internal fertilization now, and that goes along with this style of reproduction. Those are alligator lizards, by the way, and it doesn't. That's as violent as it looks. He grabs her, he bites her head, holds her down, and then mates with her. And when it's done, she has these bleeding sores on the top of her head. Anyway, it gets done. These are hemipenes. These are on male lizards or snakes as well. This is the copulatory structure that had to start developing. Once we have internal fertilization, we need a copulatory structure. This is just a great fossil from China. You say that like Trump says it, China. Completely off topic, and I hesitate to say this, I just reading the news this morning. We're at risk of a fascist takeover in this country. There are fascists in our government right now. Political point for the day. Now we're back on class stuff. These are the eggs. This is the animal sitting on. That's the mom or the dad. I think it's a remarkable fossil. We'll come back though and talk about dinosaurs. That animal, I saw this fossil. It's from China, but it was at the American Museum in New York when I was there once. It's probably gone back to China now. It's about this big as a piece, and it's just the most evocative fossil. This just transported me back to the Mesozoic. This animal was sitting on her nest when she was buried in a sandstorm, and her arms are covering her eggs. That's the mom's last act, was protecting her nest. I don't know, just transporting me right back to that day. Another thing that becomes really, really important is water conservation. If we're going to move away from water, we need to be able to conserve the water we take. And some of you have certainly seen a frog or a salamander, maybe you had a pet one. You've got to keep them damp. They have very poor water conservation adaptations compared to an amniote. So we need things like a waterproofing layer. And amniotes, our skin goes dry and dead. Scratch yourself, you're an amniote. You're touching dead waterproof. This is a dead waterproofing covering that you have. It's like 20, 30 cell layers thick of flat, dead cells. Remember 2 weeks ago in lab we looked at squamous epithelium? That's this. That slide was probably the palm of somebody's hand. But this is a waterproofing layer. And it lets us move away from water because we can conserve the water we're carrying. If you look at a cross-section of amniotic skin, this is a reptile. We develop features in our outer epidermis that protect us from water loss. Reptiles have scales. Diapsids have scales. And fish also had scales, but it's just worth pointing out here. Fish have scales. Diapsids have scales. They're not the same thing. They're completely different structures that have different evolutionary origins. Fish scales, which we didn't talk about a lot when we talk about fishes, and we don't have time to talk about everything. Fish scales are made of bone. That's part of the skeletal system. An amniote scale is actually part of the skin. It's completely different. It's not a bony structure at all. So fish scales are dermal, that just means bone. Amniote scales are epidermal, they're part of the skin. So even though they look the same, they're not related evolutionarily at all. Now, we've touched this pond before, but let's get back into it. Like I was thinking about that. This is keratin. This is a protein. And grab your hair, touch your skin, click your fingernails. This is keratin. And keratin we see in amniotes. We see keratin in fishes, we see it in amphibians, but it's not, as I said right there, it's not widely employed. We see it, but it's not a big deal for fishes. It's not a big deal for amphibians. Those structures you saw in the mouth of your lamprey, those are made of keratin. This is the foot of an amphibian that digs. It's a burrowing toad, and it has a little shovel-like structure, a little tool to dig into dirt. on the back leg that's made of keratin. And this fish has keratin knobs all over his face. The male, and when he's getting ready to breed, he grows these for pushing other males around. So keratin's there, it evolves early, but it's not widely used. Amniotes take this very useful protein and go to town with it, and it's all over in what we do, particularly in our skin. So reptile scales are made of keratin. Vert feathers, which are just another kind of reptile scale, are made of keratin. You know, you burn hair, you burn feathers, it's a horrible smell, right? That's the smell of protein burning. Hair. Mammals take that basic structure and turn it into fur. And you, if you touch your skin, you're touching a layer of keratin. It's a waterproofing layer, and it's dead. And you're sloughing it off all the time. So useful protein. Respiration, again, this is anatomy. We don't do a ton of anatomy in certain areas here, but a little bit is worth looking at. Amniotes go for a more efficient respiratory system. And amniotes, this is a lungfish. I think you recognize a frog. They're breathing here, and we talked about this a little while ago. This is positive pressure breathing. Just swallowing air and forcing it down into the lungs. And then letting it back out. That's positive pressure breathing. Negative pressure breathing is what amniotes do, certainly all living amniotes. And here we expand our chest cavity, creates a vacuum in here, and the air is pulled into the lungs. So we breathe by expanding the chest cavity. We don't breathe by pushing the air down. And that's a more efficient way to breathe, apparently. These are animals with higher metabolism. Higher metabolism requires more oxygen. We have a system to acquire that oxygen. One of the things amniotes give up on as they waterproof themselves and move away from water is they give up on gill breathing. There are no amniotes breathe with gills, even as larvae. I can't think of even any amniotic larva that breathe with gills. So salamander gills, tadpole gills, no gill breathing anymore. And since our body is waterproof, we can't breathe through our skin. If we waterproof our body, we also gas-proof it. And so, remember in frogs, amphibians did a lot of respiration through their skin, cutaneous respiration. And there's actually, in modern amphibians, there's a special circulatory element, special circulatory system that heads out to the skin so they can breathe with their skin. This is something that doesn't work with this dry, dead skin. So cutaneous breathing is abandoned. It's all through the lungs now. I've made this point, but I'll make it again. When we see modifications to the circulatory system, we almost always see parallel modifications to the respiratory system, or vice versa. They come very close. They're very closely linked. So the circulatory system, and these are just hearts here: a fish heart, an amphibian heart, reptile, and birds, modified reptile, mammal. And we've touched upon this before. Fish circulatory system, and this is a fish with lungs. Single circuit system, one pump, one circuit. And that works, but fishes are cold-blooded. They don't have particularly powerful metabolisms. As we move up on land, we're now going to lung breathing almost exclusively. And we see a modification circulatory system. We still have one pump here, one pumping chamber, but now we have two circuits. We've got blood going to the body and then coming back to the heart, then being sent in a separate circuit to the respiratory tissue and back to the heart again. Two circuits, one pump. And that's a typical amphibian system. It's a typical reptile system as well. More efficient, but further development in birds and mammals, we've got the two-pump system. Two-pump, two-circuit system. We'll come back to this. We see shifts as we move away from water and how waste is handled. aquatic things like fishes, and we've talked about this, we call them metabolic wastes, the wastes that circulate in the blood, are eliminated mostly through the gills. As the blood flows through the gills, those are dumped into the water. They're swimming in the sewer. This is evolution of kidneys in different vertebrates. When we move up on land, eliminating your waste through your gills doesn't work anymore. And so we need another system to take over, and it's the kidney system that takes over. And in amniotes, the kidney, what we call the urogenital system, become the waste elimination system. In fishes, waste elimination is handled largely through the gills. And the kidneys, we'll look at kidneys today. Remember, we looked at lampreys and hagfish last week, and I told you to find the kidneys. They're not very big, are they? They're little strips of tissue. Be sure you find them again today in your bony fish and in your shark. They're not very big. They're about water balance and salt balance, not about waste elimination. And then we already talked about this. We talked about jaw rearrangements as a trend we see as we go from primitive amniote to more advanced amniotes. See the jaws jerked around. And we see changes in locomotion. We'll talk about this when we talk a little about reptiles, but for example, we see more primitively legs out to the side, like this. And as we get more and more advanced animals, both in the synapsid lineage going to mammals and the diapsid lineage going to all the reptiles, we see the legs pulled around under the body. They're now under the center of mass. This is a more efficient way to manage that weight. That works, but it's not going to work for a really big animal very well. We see sprawling and more upright. That's one of the trends we see. And this, I thought, was interesting one day. I was at a meeting, and this is a coelacanth. It's a lobe-finned fish. And there are the lobes that are going to give rise to arms and legs. Legs and legs. We're talking about, more primitive animal. That's the evolutionary raw material. And this clip of video like this was showing, and there's those pectoral fins, pelvic fins. And the lobe-finned fish moves them to position himself in the water. And the scientist was there who his expertise was the evolution of walking. And he studied how salamanders walk, because the salamander walk is the most primitive walk we still have with us. It's called gait, the gait. And he looked at this, where is it? And he said, wow, that is exactly how salamanders move their legs. So early terrestrial walking is inherited from how these lobe-finned fish swam. I think that's interesting. Okay. It's longer than I thought. Let's take a couple minutes here. And I'm going to go find a drinking fountain. And we'll push on. We're almost done with this, and we'll start talking about reptiles. So put your pencils down for a few minutes. Think of some questions. And we'll move on. Okay. You can watch the coelacanth.